Hello, my name is Bryce Harrop, and today I will be sharing some results from work my collaborators and I have done for the Waxum project regarding the conservation of dry air, water, and energy in CAM and its impact on tropical rainfall. CAM uses a hydrostatic moist pressure as its vertical coordinate for its physics parameterizations. During these parameterizations, CAM assumes the hydrostatic pressure and hence the total mass of dry air plus water vapor remains fixed. As a result, any change in water vapor mass owing to model physics results in a spurious change in dry air mass that must be corrected later. In CAM, this correction is taken care of by an adjustment procedure that runs after all the physics parameterizations have completed. An example: if condensation results in rain falling out from the column, there would be a spurious increase in dry air mass to balance the water vapor mass lost to rain. But here's where it starts to become problematic. The latent heat release from the condensation is applied to the total mass, including the rain mass that has just exited the column. At the end of the physics parameterizations, when the adjustment is performed to correct the total mass, the energy that went into heating the spurious dry air mass is simply thrown out. Nominally, one might think of this as the rain carrying energy away, but instead of giving that energy to the land or ocean, the model ignores it. While these mass changes are small, the energy tendencies associated with the adjustment are not. The column energy tendency associated with the adjustment was recently shown by Lauritsen and Williamson to be on the order of tens of watts per meter squared, as can be seen here. This figure on the right is the annual mean energy tendency resulting from the mass adjustment procedure I have just described. It is large, and it has a very distinct regional pattern tied to areas of net evaporation or condensation because the adjustment itself is fundamentally linked to the treatment of water vapor. To test the impacts of such a large regional energy error, we run an experiment where we quote-unquote give back the energy lost. In this experiment, the energy lost to the mass of rain is simply applied to the dry air and remaining uncondensed water vapor. In other words, it would be as if we applied the latent heating to the mass of air remaining after condensation. Conceptually, this is like moving toward a framework where only the dry air has sensible energy. The experiment also provides us the opportunity to test the impacts of the regional energy pattern from the adjustment on the model's simulated climate. We focus on the hydrologic cycle and find the differences in simulated rainfall to be profound. We have tested this experimental adjustment procedure both on the default CAM6 as well as SPCAM, a version of CAM where the deep convective parameterization is replaced by individual cloud resolving models in each GCM grid cell. Despite CAM6 and SPCAM having large differences in their control climatological rainfall amounts, their responses to the experiment are nearly the same as shown on the right. Rainfall increases over the equatorial ocean and decreases over tropical and subtropical land regions. Similar responses are observed in the daily rainfall variability. Again, there are large differences between CAM6 and SPCAM for rainfall variability in the control configurations, but their responses to the experimental setup are nearly the same. The increase in variability is roughly 50 to 100% of the control value, a dramatic increase that occurs mostly in regions where the mean rainfall was also increasing. These results suggest that the hydrologic cycle is extremely sensitive to assumptions made for the energy budget. Recall that these differences are largely the result of whether energy can be carried away by rain or not. In short, these results suggest it is no longer acceptable for Earth system models to ignore the sensible energy associated with water in its liquid or ice phases. Okay, so how would we go about doing a better job? What would that actually look like? Let's consider, as an example, the surface enthalpy flux of water. In CAM and many other models, only the terms in the blue box are included, and as shown here, they make use of constant values for the latent heats. Using constant latent heat values isn't a showstopper, and we can easily use Kirchhoff's equations to write out what the other terms in the surface enthalpy flux look like, which we show here in the yellow and green boxes. These terms in the yellow and green we refer to as the surface missing enthalpy flux because they are currently missing in CAM. Looking at the equation, it is easy to see that the fluxes in the yellow and green boxes are related to the fact that the total enthalpy flux of water at the surface will depend on the temperature of the vapor, liquid, and ice water as it is fluxed across that surface. If we look at the global mean values, using inputs from CAM6 to compute the terms in our surface enthalpy flux equation, we see that the blue term dominates. No surprise there, the net flux from the missing terms is around 1 watt per meter squared. But you can probably already guess where this is going. If instead of global values, we look regionally, we see much larger values of the surface missing enthalpy flux. On top of that, the pattern of the surface missing enthalpy flux is strikingly similar to the adjustment tendency we saw before. The magnitudes are not the same, suggesting that one cannot simply substitute the adjustment energy tendency in for these missing terms. Nevertheless, including missing terms like this should be a priority for future model development. Thank you for your attention. If you have any questions, feel free to reach out to me at bryce.harrop@pnnl.gov.